Controlling electrical power is a critical issue in an industrial facility. If controls in a facility lose electrical power, it may be impossible to operate systems and equipment safely. The safety of people would be jeopardized and equipment could be severely damaged. To avoid severe consequences during a power failure, critical systems usually have an emergency power supply system to provide enough power to allow equipment and systems to be shut down safely. A large battery, which is often called a station battery, is commonly the main component in a system that provides DC power in an emergency. To ensure that it will work when it is needed, maintenance of the battery and its associated systems must be performed on a regular basis. A primary component of many emergency power systems is the battery. A battery consists of two or more battery units, called cells, which are connected in series. A conductor is connected from a battery charger to the positive terminal of the first battery cell. Intercell connectors tie the negative terminal of the first cell to the positive terminal of the second cell. The negative terminal of the second cell is tied to the positive terminal of the third cell. The rest of the cells are connected in the same manner to complete the series circuit from the charger through each cell of the battery and back to the charger. The number of cells in a battery depends on the requirements of the loads it supplies power to. This battery has 24 cells. For identification purposes, the cells of a battery are numbered in sequence, beginning with number 1 at the positive end of the battery and ending with the last cell at the negative end of the battery. Another key component of a battery system is the battery charger. The charger converts alternating current to direct current. It provides a low-level direct current to the battery to maintain the battery at full charge. This particular charger also provides current to devices in the DC system, such as protective relays. One type of system arrangement can be explained using this simplified illustration. The illustration includes a source of alternating current, a battery charger, a battery, and a DC load. During normal operation, alternating current is delivered to the battery charger. The charger converts the alternating current to direct current and supplies it to components of the DC load, such as relays and indicating lights. The charger also provides a small direct current to the battery to maintain the battery at full charge. If for any reason alternating current to the charger is interrupted, the battery will instantly provide direct current to the entire load. It will continue to supply the load until alternating current is restored to the charger or until the battery is fully discharged. Now, while the main components of a battery system are the battery and the battery charger, a battery installation is required to include several safety-related features. One of these safety features is adequate ventilation. Batteries, when they're being charged, produce hydrogen gas, which is flammable and can be explosive. Proper ventilation prevents the accumulation of hydrogen. Because of the possible presence of hydrogen gas, smoking and open flames are prohibited in the battery area. Most DC system batteries contain an acid solution. In the event that battery acid should spill or splash on a worker, despite the use of protective equipment, a wash facility is required at every battery installation for rinsing and neutralizing the acid. To properly maintain and test DC system batteries, it helps to know the construction of the battery cell, how it works, and what can go wrong with the cell and why. Battery cells used in DC systems are typically lead-acid cells. The external components of a lead-acid cell include a container, which is often called a jar, positive and negative terminal posts, and a vent with a flame arrestor. The flame arrestor shields explosive gases at the vent from external sparks or flames. The internal components of a typical lead-acid cell include a liquid called electrolyte that's composed of sulfuric acid and water, conductive lead-based plates, and non-conductive separators. The separators insulate the plates from each other. Here the plates have been removed from the jar and partially separated to more clearly show how they're arranged. The plates alternate from a negative plate to a positive plate to a negative plate, and so on. The plates at each end of a cell are always negative, so there's always one more negative plate than positive. All the positive plates are mechanically and electrically linked together and connected to one of the terminal posts. The negative plates are also linked together and connected to the other terminal post. The most widely used cell plate design is a type called the pasted plate, although there are a variety of other designs. The pasted plate design uses porous lead compounds for the chemically active portions of the plate. This material is too soft to hold together by itself, so it's typically pasted onto a metal grid. The grid is typically an alloy that is either lead antimony or lead calcium. For this reason, some cells may be referred to as lead antimony or lead calcium cells. The chemical structure of the lead compound changes as the cell is charged and as it discharges. The electrochemical action in a lead-acid battery can be explained using this simplified illustration. The electrochemical action is a process that involves an outside source of direct current, the electrolyte, and the plates. Only two plates are shown here to make it easier to illustrate the electrochemical action. Initially, the porous lead portion of the plates in an uncharged cell is composed of lead sulfate and is gray in appearance, and the electrolyte is mostly water. The charging process and electrochemical action in the cell begins when the plates are connected to a charger and direct current begins to flow through the cell. As current flows through the cell, water molecules in the electrolyte are broken down into negatively charged hydrogen gas molecules at the negative plate and positively charged oxygen gas molecules at the positive plate. At the same time, electrons transfer from the positive plate through the DC circuit to the negative plate. Sulfuric acid that has been trapped in tiny pores of the plates is driven off the plates and into the electrolyte. This increases the concentration of acid in the electrolyte. The negative plate remains gray, but it changes into a pure spongy lead with a negative charge. The positive plate turns dark brown or black as it changes into lead peroxide with a positive charge. When the cell is fully charged, additional current will no longer change the plates, but it will continue to break down the water molecules to produce hydrogen and oxygen gases. These gases bubble up and leave the cell through the vent. This phenomenon is known as gassing, and it has several undesirable effects. It causes water loss, which lowers the electrolyte level. It also produces flammable hydrogen gas. If the gassing is violent enough, it may dislodge the lead from the grids. To minimize these harmful effects, charging current is kept at a relatively low level. When a load is applied across the cell terminals, the electrochemical action reverses its process and the cell begins to discharge. When the cell discharges, direct current reverses its direction of flow. Electrons transfer from the negative plate through the DC circuit to the positive plate. At the same time, sulfuric acid leaves the electrolyte and combines with the lead in both plates. This reduces the sulfuric acid in the electrolyte and increases the concentration of water. As a result, the negative plate changes from pure spongy lead back to lead sulfate, and the positive plate changes from lead peroxide back to lead sulfate. If the charging and discharging process isn't controlled, the electrochemical action in the cells will cause problems that can reduce the life of the battery. The ability of a battery to provide the backup power that's needed when it's needed depends on maintaining it at or near its rated in-service values. When talking about cell and battery voltages, it's common to refer to their open circuit voltages. Open circuit cell voltage is defined as the voltage measured across the terminals of the cell with no connected load. The open circuit voltage of a fully charged lead-acid cell is about 2 volts, regardless of the size of the cell. Since the cells are connected in series, the open circuit battery voltage is the sum of the open circuit cell voltages. For example, this battery has 24 cells, so the battery voltage is 2 volts times 24 cells, or 48 volts. Now, a common maintenance task for batteries is to measure the cell and battery voltages. However, the voltages are measured while the battery is in service. In other words, while the battery has a connected load. In-service voltages are different from open circuit voltages. The reason for the difference is that an in-service battery has a constant charge applied to it by a battery charger to keep the cells at full charge. This constant charge is referred to as a float charge. The float charge voltage per cell is slightly higher than the open circuit cell voltage. A typical float charge voltage is 2.2 volts per cell. So, the in-service cell voltage for this battery, measured across the terminals of one cell, should be 2.2 volts. And the in-service battery voltage should be 2.2 volts times 24 cells, or 52.8 volts. Now, in-service cell voltage is one indication